It's a shared fate. I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. I want to talk to you guys about a topic known as Fourier analysis. And, well, that's not really accurate. We're not going to talk about Fourier analysis today. We're going to talk about how to build a function from a sum of sines and cosines. The topic of Fourier analysis is much broader than that. And this all goes back to, I don't know, I'm not sure when this all started, but certainly Fourier was instrumental in pushing this idea to the forefront of mathematical physics and so forth. In about 1806 or so, he made some, at the time, wild claims about functions being able to be expressed in terms of sines and cosines as a means to solving something called the heat equation. If you take Math 334 here, you'll actually see that put into practice. We use Fourier series to solve problems like waves on a string, or the propagation of heat in a bar, the solution to Laplace's equation, for example, finding the voltage function on a plate, like a metal plate, where the voltage on the edge of the plate has been fixed, or things like that, or even the propagation of electromagnetic waves in a waveguide. All of these things are ultimately understood by a mixture of what's called partial differential equations, which I wrote for some of you, and Fourier analysis. These two tools go together to solve a vast array of applied problems, many of which are interesting to engineers and also scientists. So that's why I'm talking about this, just to get us started, because Fourier analysis is a deep and interesting topic. It's also what underlies a lot of the way that you listen to music. The idea of a Fourier analysis of music basically is to take a note, take sound, break it down into its constituent frequencies, and sort of give a sort of a DNA, if you will, for sound, of how to build the sound back from just knowing the constituent frequencies and so forth. So that in a nutshell is what Fourier analysis is about. But again, we're going to look at a much more concrete question here to start with, which is, if we look at, excuse me, f of x equals to x on minus pi less than x less than pi, all right? So look at that function. Pretty simple function, right? Not to scale, obviously, but maybe I should try harder to... Let me try to actually draw a line with slope 1. Surely I can achieve a line with slope 1 today. So what I want to do is explore, can we recover f of x equals to x using a sum of sines and cosines? All right? I mean, this is essentially Fourier's madcap claim that you can write f of x essentially as the sum of an cosine nx plus bn sine of nx, n equals 1 to infinity. Okay, fine, a constant. All right. Now, let me, I have a PDF that I've posted in course content for you guys, all right? And this is actually a electronic supplement to Stewart's calculus, of course, which is a popular and well-known calculus text. And this PDF is posted online. I have a link in the course planner to it. Right, the PDF's also posted. This is actually, at the moment, equation 2 in that PDF, all right, if you want to read that later. And I've assigned you some homework problems from that PDF as well, right? So, all right. So this is the idea that we can build f of x equals to x using a sum of sines and cosines somehow, right? And here, yep. Same n, yeah. So, I mean, there's some parentheses here. I mean, that, so yeah, to be more pedantic here, this is like a0 plus a1 cosine x plus a2, oh, excuse me, good grief, b1 sine x plus a2 cosine 2x plus b2 sine 2x. And we'd be here all day if I had to write the whole thing, but so this is called a Fourier series, or sometimes it's called a trigonometric series because, well, why do we call power series a power series? Why is it a power series? What is it a sum of? It's a sum of what kind of functions? I mean, what is x to the power n? This is a power function, right? So a power series is a sum of power functions. A trigonometric series is a sum of trigonometric functions, right? Now our goal, our mission, should we choose to accept it, is to find values for the Fourier coefficients. We need to choose, calculate, purchase, whatever you want to do, values for the Fourier coefficients, which are a0, a1, a2, dot, 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 and b1, b2, b3, dot, dot, dot. All right? That's our goal here. The way that that's done is really neat. So it basically comes down to this fundamental observation. In terms of the calculus involved here, which is that if we integrate, all right, cosine of nx times the cosine of, let's say, px dx, we get a very particular thing. And if we integrate the cosine of nx times the sine of px, we get a very particular thing. And if we integrate the sine of nx times the sine of px, we get a very particular thing. These are all, and well, okay, fine. I haven't really done it justice yet. It's not just not just the integral. It's actually the definite integral we're interested in, and the definite, yeah. Is it what? There's no b naught because sine of 0 is 0, so no need for it. There's an asymmetry between sine and cosine in that sense, yeah. Because cosine is even, but sine is odd, and a odd function with 0 in its domain automatically takes the value of 0 at 0. So for these integrals, the context matters here, and so what we're actually interested in, the observation is about the integral from minus pi to pi, minus pi to pi, minus pi to pi, all right? So let me do one of these integrals, and once we do one of these, we'll be able to tell what happens for the other ones. You guys, which of the first, you guys pick for me. Which one do you want me to do, either the first one or the third one? What's that? Third, okay. Okay. It's not a bad choice. All right, so can you guys remind me how we integrate? Well, I'll do the third one. So I mean, in case you've forgotten, maybe you have this memorized by now. I don't know. I don't have it memorized, so I'm going to have to rework it back out again. So I'll use imaginary exponentials. This is 2i e to the I n x minus e to the minus I n x, you know? 1 over 2i e to the I p x minus e to the minus I p x. And that works out to minus 1/4 e to the I p plus n x plus e to the minus I times n p plus n, or n plus p, you pick it, x, excuse me, minus e to the I times n minus p x plus e to the minus I times n minus p x. So I'm multiplying the terms out, and I'm grouping them so that maybe we can see the cosines that are underlying what's going on here. I mean, this is 1/2 of 1/2 e to the I n minus p x plus, yeah. Oh, these are both minuses. I'm sorry, both minuses here, right? Plus e to the minus I times n minus px minus 1/2 e to the I p plus n x plus e to the minus I times p plus n x. So I'm just working through the trigonometric identity that we need to integrate these things, right? Which is part of the reason I like this lecture, because it's another helpful review for the final, right? Because I might ask you to integrate that on the final exam. Could you do it? I don't think you can, unless you know the bit of trigonometry I'm sharing with you right now, right? Which is that this is actually 1/2 of the sine of n minus p times x minus the sine of n plus p times x. Did I say sine? What do I mean? Yeah. Sorry, it's a cosine. Let's see, whenever I do something like this, I always try to check my answer. How can you check if this is right? How about if we put, as a check, if we put nx equal to pi over 2, and we put px equal to pi over 2, and by the way, I'm an idiot. I should have derived this identity with nx equal to theta and px equal to beta. That would have been a lot less writing, right? Like, why derive the identity with all the symbols when you could derive it with less, Sorry, poor planning on my part. But if we set nx equal to pi over 2 and px equal to pi over 2, we know sine of pi over 2 is? We know, I know that laugh. It's Dr. Wing. Anyway, so sine of pi over 2 is 1, right? So if my formula is right, if I haven't made an arithmetic mistake somewhere, we should be able to get 1 equals to 1 on both sides, right? Does it happen? What happens when we put over here? We get what? Cosine of 0, right? Which is 1. And over here we get cosine of pi, which is minus 1. Minus 1 is 1. 1 plus 1 is 2. 2 over 2, 1. Good, it checks. All right. So a little bit of a refresher right there. Now let's do the integral. Integral from minus pi to pi. And we're assuming what? Let's assume that n is not equal to p for the sake of a step I'm about to make. N not equal to, n not equal to p. So we got sine of nx, sine of px dx equal to 1/2 integral from minus pi to pi of cosine of n minus p x minus the cosine of n plus p times x, right? You'll forgive me if I skip a parenthesis there to reduce the clutter a bit. We haven't even found, I haven't even filled in the blank here. I said that this is something interesting, this is something interesting, this is something interesting. We're no longer checking. Fair enough. I said the check in words. I said that if we plug in this, if we plug in those into what I've derived, we get 1 equals to 1, so it's good. More specifically, we get 1 is equal to 1/2 of 1 minus a minus 1, which is 2 over 2. Okay. All right, so you guys can integrate this, right? What's the integral of cosine? Right? Simple u substitution makes us divide by n minus p or n plus p, right? Cosine integrates to sine, right? What happens when you plug in pi or minus pi into these expressions? Do I need to write it out? Or can we talk about it? Let's talk about it. When I plug in pi, I've got sine of n minus p times pi, or n plus p times pi. Either way, we're looking at sine of an integer multiple of pi, which we know is 0. And similarly, minus pi, again, integer multiple of pi, integer multiple of pi, so 0. The answer is 0 if n is not equal to p.
Why are we assuming n is an integer? Is that just like...
That's the setup.
We're just setting it up.
That's part of Fourier's starting point. Just like we take a sum of integer powers, we're taking a sum of these kinds of cosines and sines.
So n can't be like a decimal point.
No. In differential equations, we do study a generalization of power series where we take non-integer powers. This is called the method of Frobenius. Frobenius type series have very different convergence behavior than the power series you've been shown. But that's a little bit off track. Now, there's another case, though, right? What happens when n equals p? What about n equals p? So we'd have what? Cosine, sine squared, right? Of px, am I right? See, if p and n, or we could keep the n, keep the p. What do you guys? You want me to keep the p or keep the n? Keep the n. Ah, you're making me erase. All right. Oh man, someone had to be away today for a track meet, and I promised him I wouldn't give a quiz today. I told him it was a great personal sacrifice for me because I felt like there was a chance Zach wasn't going to show up. And Zach-based comedy gives me joy. So I should give you guys a quiz and then arrange for the quiz to be. His was excused. I see. So you're telling me Zach has no excuse. Okay. Yeah. And I don't mean in the technical sense. I mean in the pejorative sense. Let's hear. 1/2, 1 minus cosine of 2nx, yeah? So this trig identity, you better not need to derive. You better know this one, right? Because if I ask you integral of sine squared, you should not have to. You should know how to integrate sine squared, right? I mean, that is a shame on me if that's not on the final, right? Shame on me. And then, so that would be 1/2 x minus 1 over 2n sine 2nx evaluated from minus pi to pi. What happens here? Well, again, this guy goes to 0 because it's just a sine of multiple of pi. But the x gives us something. What does it give us? It gives us pi. It gives us pi. So this is the case-wise defined story. We get 0 if n is not equal to p, and we get pi if n is equal to p. All right? And I would argue that this is the right place to talk about this material because these calculations are native to Calculus 2. This is Calculus 2, right? Now, similarly, guess what? This also works out just the same way. 0 for n not equal to p, and pi for n equals to p. And the middle one, you know what happens when you integrate cosine times sine? I got a pi. It's always pi. Here, let me give you an analogy. If we have f of x, g of x, we can define this to be the integral from minus pi to pi of f of x, g of x dx. This is what I'm writing down is, this notation here, it's read inner product of f of x and g of x, all right? In Calculus 3, and maybe already in this course, I defined a dot b, right? I haven't talked a lot about it. It happened, and then we moved on, right? But the dot product of two vectors is another example of a quote-unquote inner product. What does it mean if the dot product of a and b, if two vectors' dot product is 0, what's that say about them? They're perpendicular, right? They're orthogonal vectors. Orthogonal is just another word for perpendicular in the abstract sense. So these integrals are actually taking the inner product, quote unquote, of sine and cosine. And what these results mean is that cosine of different arguments are perpendicular. The only way that cosine can be in the same direction as another cosine is if they have the same argument, all right? In which case, their inner product is pi. In some sense, that says that the length of cosine is the square root of pi, quote unquote. And likewise, this middle one, actually sine and cosine are orthogonal. They're in different directions in function space. So that actually works out to 0. So, you know, what we'll learn in Calculus 3, among other things, is that we can take a vector and we can decompose it into its components by taking inner products, by taking dot products. Like if we have A is equal to A1, B1, A1, A2, right? Then A dot, the vector 1, 0, is A1. And A dot, the vector 0, 1, is A2. So this is a general idea. We can select components by taking dot products. By analogy, we can select Fourier components by taking inner products. That's the idea here. So this is a bit of a jump, but we expect, so we have f of x equal to a sub 0 plus the sum n equals 1 to infinity of a n cosine nx. I'll write it as 2 plus the sum, I'll break up the sum, bn sine of nx, right? So if we want to select, so the numbers a0, a1, a2, b1, b2, b3, so forth, these are playing the same role for the function f of x that a1 and a2 play for the vector a. So if I want to select the components, I take the inner product of the function with the basis, so to speak. What I'm trying to get at here is if I calculate the inner product of f of x with cosine nx. So I guess I should mention, guys, in another notation, this is really just inner product of cosine nx and cosine px if you so that, if I calculate this, I should expect that that is going to give me, a0 with cosine nx and, oh man, I'm sorry, I need to make this n into a p. I'm making this one into a p, so a0 cosine p. Oh no. I should probably drop back to integration. I think I'm losing you guys using this other notation. So all I've done, here, I'll do the other. Let me make the similar statement for sine in terms of integral. So if I integrate from minus pi to pi, f of x sine of px dx, it should be equal to the integral of Pac-Man. What do I mean by Pac-Man? I am calling this thing up here Pac-Man. All right? So if we integrate Pac-Man, we can break it up into the integral of each part of Pac-Man, all right? So what I mean is, integral from minus pi to pi of a0 dx, yeah, plus, and I can pull the sum out of the integral. I mean, I'm making a step here, kind of like our term-by-term integration theorem. Oh, I'm sorry. What was this? I forgot my sign. Most of this is 0. Most of this is 0. What do I mean? So let's suppose p is not equal to 0, okay? Suppose p is not equal to 0. Then what happens? This is the integral of cosine over a full cycle. So this is 0. This is 0. This is either 0 when n is not equal to p, or it's pi when n is equal to p. So what survives of all this stuff is just pi a sub p. That's all that survives. And down here, integral of sine over a full cycle is 0. This is 0. This is 0 when n is not equal to p, right? I mean, I should be more specific. This is Yeah, okay. So this is 0 when n is not equal to p. So this is actually just equal to what? Pi b sub p. So in summary, we find that the formula is a sub p equal to 1 over pi, the integral from minus pi to pi of what? Well, f of x cosine of px dx. That's what we just worked out. Right? Now, I don't really like p, so I usually rewrite this formula with n. All right, so I'm gonna scratch out the p and write an n instead because it's just, I don't know. I just like working with n. That's just bookkeeping, right? So there's a formula. We can calculate the Fourier coefficient by taking this integral of f of x. And likewise, b sub n, 1 over pi, integral from minus pi to pi, f of x sine of nx. What about a sub 0? How do we calculate a sub 0? What if we take 1 inner product with, f of x inner product with 1? What happens there? I'm sorry, I'm still messing it up. What if I take the inner product of Pac-Man with 1? So these pieces, the cosine and sine pieces integrate. So my argument in short, I don't want to write it all out because I'm going to run out of time if I do. These integrate to 0. We just have the integral from minus pi to pi of a sub 0 dx is what it boils down to, which of course is 2 pi a sub 0. But on the other hand, this should be equal to 1 with f of x, right? So this leads me to the formula a little bit different, but a sub 0 is 1 over 2 pi, the integral from minus pi to pi f of x dx. Because the integral of yeah. All right, so these are in the PDF I gave you guys, and oh man. Oh, yes. So what I've just derived are equations 3, 5, and 6 on page 2 of the PDF, all right? Now what I want to do is I want to put these into practice on the example, right? Let's apply this formulas we found to, what does this look like when we do this for x? Yeah? What happens when we do it for x? I'll do the easy one on this board. Let's calculate a sub n. 1 over, so let's, apply to f of x equal to x. So 1 over pi, integral from minus pi to pi of x times cosine of nx dx. What's that integral? Again, I really like this topic for the end of this course because it gives me a chance to talk about things on the final. Like, this is one of the things we should have learned. If we have an integral of a odd function about a symmetric interval of the origin, it could have a non-zero integral, right? But if we have an integral of a, well, actually, what happens if this is an odd, what happens when you integrate an odd function about a symmetric interval of the origin? What does it work out to? Yeah, that's 0. And likewise, a sub 0 is equal to 1 over 2 pi integral from minus pi to pi of x dx. Here, I'll even work this one out explicitly. This is 1 over 4 pi x squared evaluated from minus pi to pi, which again is 0. We didn't really need to do this because it was the integral of an odd function about a symmetric interval of the origin, so we know that works out to 0. This is also part of a deeper intuition that I hope you're starting to gain, which is that even things are built from even things. So we're trying to build a Fourier series for the odd function f of x equals to x. It's not surprising that the even parts of the expansion are trivial. Was it a question?
I didn't think cosine started it.
You didn't think the cosine started it?
It doesn't go to the origin twice.
But, well, this is an odd function, though, because, well, x goes to 0, though. So x times cosine, I mean, when I plug in 0, the x makes it 0. Yeah, yeah. And more generally, the thing is, if I have an odd function times an even function, the result is an odd function, which was my thought process there. In contrast, this guy is going to be x times sine x, which is odd times odd. That gives me an even function. So the integral of an even function about the origin, symmetric interval about the origin, doesn't have to be 0. In fact, we're going to calculate it. Let's calculate that now. Let's see here. So b sub n, 1 over pi, integral from minus pi to pi of x times the sine of nx dx. How do we do this integral? There is so much calculus 2 in Fourier analysis, isn't there? Because this is integration by parts, with bounds no less, right? Something that you guys needed to work on last time we revisited it. Now, some of those who needed to work on it have since left us. Yeah, 1 over n, x cosine nx minus the integral of 1 over n cosine of nx dx. I have to evaluate from minus pi to pi. All right. All right. I'll remove these to reduce the clutter a bit. Anyway. So what happens here? We have 1 over n pi cosine n pi, right? Minus pi cosine n pi. Good grief. Minus n pi. Except I haven't done what? Is it minus? It's actually plus, right? Because it's minus a minus, which is a plus. Because of the fundamental theorem of calculus here, that's a plus. And this integrates to what? Really plus 1 over n squared sine of nx evaluated from minus pi to pi. Integral of cosine is sine, but sine over nx. Oh, I still have the minus, don't I? I can't integrate. Fortunately, that sign error wouldn't have cost us anything in the final. Uh-oh, what'd I do?
I'm sorry, I just missed what you said.
Because we evaluated the upper limit. I mean, so quote unquote f of pi minus f of minus pi, so to speak. But the f of minus pi has, when we plug in minus pi, it's got minus pi there. But then this minus compensates that minus to give me a plus, which is good because otherwise everything here would be 0. So this is 0 because sine of pi and sine of minus pi Any multiple of them is 0. This, on the other hand, is 1 over n pi times 2 pi cosine n pi. What is cosine of n pi? Cosine of n pi is minus 1 to the n. So, see, because if we put in 0 or 2 or 4 or any even number, we get 1 for cosine of an even multiple of pi. But cosine of any odd multiple of pi is minus 1. That's the same as minus 1 to the n. So this is just minus 1 to the n. The pi's cancel. We get 2 times minus 1 to the n over n. So there you go. It took us a class period because we were deriving some things, but yep.
I don't understand what we're trying to do though.
I was about to say that. So our goal, again, was to express f of x equals to x as a sum of sines and cosines. The calculations we've done have revealed that we don't need cosine, we don't need a constant. We apparently can build we can build the x function from just a sum of sines with those coefficients. So the b sub n is this, right? So the claim actually works out to the following. I can be more precise. So like what's b sub 1? If I haven't made a stupid mistake. Huh, so start that, all right, fine. So yeah, looks like minus 2, right? So minus 2 sine of x. Then what's next?
Why are you putting sine of x in front of the 2? Is that just because b of n is the coefficient?
Yes, b of n is the coefficient. How about b2? What's b2? It's 1. So plus sine of 2x. What's next? N equals to 3. What do I got? Yeah, 2/3 sine of 3x. What's next? 1/2 plus 1/2 sine of 4x. Please work. Please work. Yes.
So why are they trying to make f of x equals to x out of sine and cosines?
Why are we trying to write sine as a sum of sines?
Yeah, like what is like
This is the idea of Fourier, to rewrite a function as a sum of sines and cosines.
because we can. Why not?
Again, there is an application actually explicitly discussed in the PDF that I've posted for you guys. Yeah, let's get a new one.
Do you still have the clip illustration?
All right, let's try this out here. So y equals x. Great, there it is, right? And let's see here. What did we want? Minus 2, what was it, 2 sine x? All right, well, that doesn't look very helpful. Then what was it? Plus what? 2 sine 2x. Huh. Minus what? I start to think I have a sign error. What was the next one? 1/2, did you say? Ah! Get back up there. Huh. That is suspiciously looking more and more like that. Where have I made... Where is my sign error? It's got to be in here. Oh, what's the integral sign? There you go. Oh, you should have said that. It would have been nice. It's not okay. This is. Oh, you had your hands for a few minutes? Where? Oh, I think it must have been behind Drew's head. That's my excuse. I'm sorry. Oh, it's okay. So, look. There's a minus here, but I can fix that, right? Put everything in. So what's next? What would the next term be? What's B5? Plus 2/5? Sine of 5x. See, and the more and more you add, the closer and closer you'll get to modeling the function on the interval. I find this very amusing because to calculate the Taylor expansion, what do we have to do to fit a Taylor polynomial to a thing? We had to take repeated derivatives, right? Somehow to find the Fourier expansion, it involves calculating particular integrals of the function you're trying to expand to describe, right? Anyway, we'll talk about this another day, but I hope you at least see the idea. Yeah. Oh, so I'm not going to be here next Tuesday or Wednesday or Thursday. I know, right? But I should be here Friday. So I feel like I owe you some additional examples, right? So I'm going to try to either link you to a video of yesteryear or make some new videos for you. If there's something in particular you'd like to see me work out, email me so I can think about it this weekend. Yeah. Yeah, we won't have class. Is that okay? Yeah, okay. But you're welcome to come here and work together. You know? Oh, this is important. Don't tell Zach.